Hello and welcome back. In this segment, we will talk about BlockCypher modes of operation. The suggested read for this segment is chapter 3.6 in the book of Katz and Lindell. So in the last lecture, we've introduced block ciphers and pseudorandom permutations, and we've seen some candidate constructions of these, but these objects are primitives or building blocks. A block cipher is not an encryption scheme. The kind of security that it gives is that of a pseudo-random permutation. It's indistinguishable from a random permutation. That doesn't mean it's an encryption scheme in the sense of insecurity or in CPA security. So the question is, given a block cipher, how do we construct encryption from block ciphers or pseudorandom permutations? Constructions that use block ciphers as a black box to build encryption schemes are typically referred to as modes of operation. And in principle, we use these to encrypt very long messages. So assume you have a long message M, and it can be chopped into blocks of size security parameter. That is, if you have a message M, you chop it into blocks M1, this is of size security parameter M2 and so forth until MT. It might be that the last message doesn't fill the last block entirely. What we do in this case is we typically just pad it. For instance, with all zeros or with a terminator symbol. Let's say we pad this with 0 to the K. One of the first modes of operation that was proposed for block ciphers is the so-called electronic codebook mode, or ECM. In this mode, given message blocks M1, M2, M3, we encrypt by passing them through the pseudo-random permutation or block cipher FK, obtaining ciphertext blocks C1, C2, and C3. So this mode of operation does the most naive thing imaginable. To decrypt, we just use the inverse of the pseudo-random permutation. So for this mode of operation to be correct, you actually need a pseudo-random permutation. A pseudo-random function is not enough. This mode of operation is not INCPA secure. Well, it is not even insecure. And in fact, it should not be used anymore. There are some very specific use cases where it is justifiable to use the electronic codebook mode. For instance, when you need to be able to compare ciphertexts or compare encrypted messages by just comparing the ciphertexts. This is a situation in which it can be justified to use this mode, but also for this use case, there are better solutions these days. This can be seen in this quite famous example from Wikipedia. Take an image, here this Tux penguin, and chop it into blocks of size 256 bits. As a matter of fact, if this is a JPEG image, it comes in blocks of 256 bits. If you encrypt this under the electronic codebook mode, you will get a ciphertext that looks like this. So if you take the ciphertext and just interpret the ciphertext as a JPEG and then render it, you will see this. Clearly, a lot of information about the plain text is still present here in the ciphertext. Whereas if you use a good cipher or an insecure cipher, what you will see is something like this. It just looks like white noise. So while we think this electronic codebook mode is a thing of the past, it recently became known that Zoom, the very service we use to host our Q&A sessions, actually used the electronic codebook mode to encrypt its videos until very recently. The second mode of operation we look into is the so-called cipher block chaining mode, or CBC mode. How does this work? First, a so-called initialization vector, or IV, is chosen uniformly at random. This IV will be part of the ciphertext. Now take the first message block and M1 and XOR them together and run this through the pseudorandom permutation, obtaining a first ciphertext component C1. And now instead of using an initialization vector, we just let C1 take the role of the IV. So we XOR C1 onto the second message block, M2, and pass the result through the pseudorandom permutation, obtaining a ciphertext block C2, and so forth. First, this mode of operation is in CPA secure if the initialization vector IV is chosen uniformly at random and if F is a pseudorandom permutation. One drawback of this mode of operation is that encryption cannot be performed in parallel. So even if you have a super parallel computer, you first need to encrypt M1, feed the cipher back, XOR it onto M2, then encrypt this. So in this mode of operation, encryption is somewhat slow. However, decryption can be done locally. For instance, let's assume we just want to decrypt C2. What do? Well, first we invert the pseudo-random permutation, FK inverse, and then we just have to XOR C1 onto this to recover M2. There's a variant of this mode called the chained CBC mode. So the first time you encrypt let's say a message M1, M2, M3 with this chained CBC mode, it works just like the CBC mode. But then the second time you encrypt something, you're not choosing a fresh initialization vector, but you use C3 as the new initialization vector. So the problem with this mode is it is not in CPA secure. And the way to see this, or to think why this is the case, you might go ahead and try to figure out the attack by yourself. But the problem is that a CPA adversary, so an adversary with access to an encryption oracle, might choose M4 depending on C3. So please go ahead, try to figure out how a CPA attack on this mode of operation could work. Next, there is the so-called output feedback mode. How does this work? Again, we have an initialization vector, and this initialization vector will be part of the ciphertext. So in the first round, we feed the initialization vector into FK and XOR the result on top of M1 to get C1. Now we don't feed back the ciphertext C1, but the output of the block cipher FK and do the whole thing again. Now, again, the output is XORed onto M2, obtaining a ciphertext block C2, and so forth. This mode of operation is in CPA secure for a uniformly random initialization vector and if F is a pure F. So for this mode of operation, we don't need F to be a pseudo-random function, a pseudo-random permutation anymore. It's enough if it is a pseudo-random function. So we don't need a way to invert this function FK. However, for this mode of operation, both encryption and decryption must be performed sequentially. That means if you want to encrypt a message that consists of n blocks, you will have to do these n rounds sequentially, both in encryption and in decryption. However, there's a bit of a light at the end of the tunnel, namely the paths that come out here. Let's maybe call these, this is Z1, what comes out here is Z2, and here Z3. These values can be pre-computed before encryption. So this expensive sequential computation can be pre-computed, and then when you actually get your message, you just need to XOR these pre-computed values Z1, Z2, Z3, and so forth onto your messages to get the ciphertext. The same for decryption. You can compute C1, Z2, C3, and so forth for decryption as well. The last mode we will look into is the so-called counter mode. And here you encrypt as follows. First, you choose a uniformly random block called CTR. So what used to be the initialization vector is now called the counter. You will see in a moment for what reason we call it counter. And this is the first part of the ciphertext. So to encrypt the first block, M1, what do? We take counter plus 1, feed it into the block cipher, and XOR the result on top of M1 to get the first ciphertext block C1. To encrypt M2, we feed counter plus 2 into the block cipher and XOR the result onto M2, getting the second ciphertext block C2, and so forth. This mode of operation can be shown to be in CPA secure if the string counter or if the input counter is chosen uniformly at random and if f is a PRF. That means we don't need a way to invert FK. For this mode, both encryption and decryption are local and can be both parallelized and pre-computed. That means, in a way, in terms of efficiency, this mode of operation combines all the advantages of the other modes of operation that we've seen. How do you decrypt? To decrypt C1, what do you have to do? Well, you first take the counter, it's part of the ciphertext, compute counter plus 1, pass it through your FK to get this value here. And now if you XOR C1 and this value together, obviously you get back M1 and so forth. As a matter of fact, there really is no reason not to use this mode of operation. In a way, you can think of all the other modes of operation as just existing for legacy reason. They were used one time back, but these days the state-of-the-art mode of operation for block ciphers is the counter mode. So to recap this lecture, block cipher modes of operations provide us with a way to encrypt long messages using block ciphers as a primitive. The electronic codebook mode, ECM, provides very little security and really should only be used in very, very special scenarios, and you should be very aware of what you're doing if you use this mode of operation. The cipher block chaining mode is okay, but has inefficient encryption. The chained CBC is not okay. There is a chosen plaintext attack against this mode of operation. The output feedback mode is okay, even though both encryption and decryption need to be performed sequentially and are therefore slow, but can be pre-computed. And really the bottom line of this segment really is, if you have the choice to use the counter mode, then use it in your application. Thanks, that's all. Bye.